Hey everyone, and welcome back to The Explainer. Today we're mapping out what is honestly one of the most fascinating areas of your Cambridge International A-level physics syllabus, Section 24, Medical Physics. If you've ever sat there and wondered how all these abstract physics concepts actually translate into real, life-saving medical tech, well, you're in exactly the right place. My goal today is to make these syllabus requirements intuitive, memorable, and most importantly, ready to use on your exams. We are literally going to break down the mechanics of how we can look inside the human body without ever picking up a scalpel.
Here's our quick roadmap for today. First, seeing with sound using ultrasound. Second, peering through tissues with X-rays. Third, 3D imaging via CT scans. And fourth, antimatter imaging with PET scans. Let's get right into it.
Section 1. Seeing with sound, ultrasound.
So how exactly do we use something like sound as a medical diagnostic tool? What's great here is that this grounds us directly in what Cambridge actually expects you to know. Looking closely at the syllabus text for Section 24.1, it's not just about knowing that ultrasound exists. You really need to understand the generation, the detection, and the specific mathematical relationships governing how these sound waves interact with different tissues. You know, things like specific acoustic impedance, reflection coefficients, and attenuation. So let's unpack these exactly as you're going to need to apply them.
Okay, so it all kicks off with this genuinely brilliant phenomenon called the piezoelectric effect. To generate ultrasound, step 1 is applying a rapidly alternating potential difference, or PD, right across a piezoelectric crystal. This electrical signal makes the crystal literally, physically change shape. It starts oscillating. Then, in step 3, these high-frequency mechanical shape changes generate the ultrasound waves that travel down into the body. But here is the absolute magic of the transducer. It actually works in reverse. In step 4, when those sound waves bounce off internal organs and come back as echoes, they mechanically compress that exact same crystal. This generates an electromotive force, an EMF, that our machines can instantly read. It's doing double duty. It's both the speaker and the microphone. Now, as those sound waves travel through the body, they're obviously going to encounter different types of tissues. And this brings us to an absolutely vital syllabus definition: specific acoustic impedance, which we represent with the letter Z. Take a look at the formula. Z equals the density of the medium, that's the Greek letter rho, multiplied by C, which is the speed of sound in that specific medium. You can basically think of acoustic impedance as a measure of how much a specific tissue resists the transmission of sound. And every single tissue in your body, fat, muscle, bone, has its very own unique Z value.
So the real question is, what happens when ultrasound hits a boundary between two tissues that have different acoustic impedances? Well, that is perfectly dictated by this formula, the intensity reflection coefficient. It gives us the ratio of the reflected intensity to the incident intensity. Just look at the math for a second. If Z1 and Z2, the impedances of the two tissues, are really similar, the top part of that fraction is super close to 0. That means very little sound is reflected. But if there's a huge difference, like say between air and skin, almost all the ultrasound just bounces right back. This actually perfectly explains why doctors slather that freezing cold gel on your skin before an ultrasound. The gel acts as a bridge, matching the acoustic impedance so the sound actually enters your body instead of just bouncing uselessly off your skin.
Moving right along to Section 2, peering through with X-rays.
All right, let's shift gears from high-frequency sound waves to high-energy electromagnetic radiation. Unlike ultrasound, which reflects off boundaries, X-rays are fundamentally designed to pass right through the body. Per your syllabus, you need to know they're produced by the electron bombardment of a metal target. Basically, electrons are accelerated across a massive potential difference and just slammed into a metal anode, releasing all their kinetic energy as highly energetic X-ray photons. You'll definitely need to be able to calculate the minimum wavelength of those X-rays based on the accelerating voltage. And because X-rays cast essentially a shadow of our internal structures onto a detector, image contrast, meaning the visual difference in darkness between different tissues, is absolutely essential for making out fine biological details.
Okay, listen up, because here is a massive study hack for your exam prep. Both ultrasound waves and X-ray photons lose intensity as they travel through matter, right? We call this attenuation. And this just brilliantly illustrates the pure elegance of physics, because the exact same exponential attenuation formula applies to both. Intensity equals initial intensity multiplied by e to the power of negative mu x. Mu is the linear attenuation coefficient of the material, and x is the thickness. So whether you're dealing with a beam of sound or a beam of ionizing radiation, the underlying mathematical logic of how it's absorbed over distance remains beautifully, perfectly consistent.
Next up, Section 3. 3D imaging using CT scans.
So, a standard X-ray is really just a flat 2D shadow. Let's demystify how a CT scan actually works to get a full 3D shape, step by step. In step 1, the machine doesn't just snap one picture. It physically rotates around the patient, taking multiple X-ray images from completely different angles of just a single, super thin slice of the body. A computer then takes over, mathematically combining all those overlapping angles to generate a highly detailed 2D cross-section. In step 2, the patient is moved just slightly along an axis, and the whole process repeats to grab the next slice. Finally, in step 3, the computer stacks all these 2D sections on top of one another to build a complete, fully manipulatable 3D image of the internal structure. It's essentially slicing the body digitally.
And finally, Section 4, Antimatter Imaging with PET Scans.
Let's see how all of this builds to the final and, frankly, the most sci-fi part of the whole medical physics syllabus, Section 24.3, PET scanning. PET stands for positron emission tomography. To get this, we need one key definition first. A tracer is a substance containing radioactive nuclei that gets introduced right into the patient's body and is absorbed by whatever specific tissue we're studying. For PET scans, we specifically use a tracer that undergoes beta plus decay. This means the radioactive nuclei inside the tracer are actively emitting positrons, actual antimatter, directly inside the patient's bloodstream. Crazy, right?
This kicks off a seriously fascinating timeline of quantum events. The tracer gets absorbed into the target tissue, maybe something like a highly active tumor. Those unstable nuclei emit a positron, which, again, is the antimatter counterpart to an electron. Because the human body is entirely full of normal matter, that positron almost instantly bumps into a regular electron. And when matter meets antimatter, total annihilation. Their combined mass disappears completely, converted instantly into pure energy. And to perfectly conserve momentum, this energy is emitted as a pair of identical gamma-ray photons that shoot outwards in exactly opposite directions. Now hold on, I want to pause here for a second, because this is a prime spot for exam calculations. The syllabus explicitly requires you to calculate the energy of those gamma-ray photons emitted during the annihilation of that electron-positron pair. You're going to use Einstein's famous equivalence principle, E equals mc squared. You calculate the combined mass of the electron and positron to find the total energy released, and then, crucially, you divide it by 2 to find the energy of each individual photon. It's just a perfect synthesis of fundamental particle physics and applied medical tech.
So what do we actually do with these photons once they're created? Well, because they're super high-energy gamma rays, they easily travel right outside the body. The patient is sitting inside a ring of detectors. Because those two photons traveled in exact opposite directions at the speed of light, the machine precisely registers their arrival times. By calculating the minuscule, and I mean microscopic time difference between when the two photons hit opposite sides of the detector ring, the computer can literally pinpoint the exact location where that annihilation occurred. By processing millions of these arrival times, an incredibly precise, colorful image of the tracer concentration is created. This shows doctors exactly where the biological activity is the absolute highest.
And that wraps up our journey through Section 24. We've gone all the way from the mechanical oscillations of ultrasound to the quantum annihilation of PET scans, mapping out exactly what Cambridge expects you to know. The structured knowledge you need is right here. So, I'm going to leave you with one final thought to ponder. How are you going to actively apply these formulas, these step-by-step sequences, and this visual logic to your very next past paper practice? Take these concepts, keep them front and center in your mind, and go crush those exams. Keep learning, stay focused, and I'll catch you in the next explainer.